Hi all, it's Mr. Yeager for chemistry, and now we're jumping into Charles' Law, which this is a bad spelling. We don't put an S after apostrophe when you have a name with the S. You just put the apostrophe after the S. All right, sorry, English lesson. All right, so Charles' Law, okay? All right, so with Charles' Law, we're going to pick another two variables out of volume, pressure, and temperature. For Charles' Law, we're going to take volume and temperature, okay? Those are the two we're going to play with now. The thing is, with volume and temperature, okay, so I'll write that out. We're looking at volume and temperature. That means pressure will stay constant, so we don't need to worry about the pressure at all this time, okay? Volume and temperature will be altered. It turns out volume and temperature are directly related. I would hope you kind of know this. If you increase the temperature of something, it wants to expand, all right? We've seen that with balloons. You take balloons into the hot air, they expand. You've seen things where obviously if you throw things into the fire, that's not Charles because they're not able to expand. That's more of a pressure thing, but the idea is that obviously they want the capability to expand. Okay, hot air balloons, they use expansion with the temperature of the air inside the hot air balloon. So there's a direct relationship between them. As one goes up, the other goes up. All right, so that's important to recognize. So with this, the idea would be you have some sort of piston, but this time the piston's not moving. It's just sitting on top. If you increase the temperature of that container with that piston on it, it'll push the piston on up. Okay, the gas particles will expand, and it's because those particles start moving faster that they're able to kind of expand it on out. What we mean by the pressure's not changing is the idea that we're not increasing the external pressure on it. We're not trying to push it. We're letting the pressure just remain the same around it. All right? So real life examples. This was an example with Deflategate, if you remember that. This is from a while ago with the New England Patriots, where the footballs were deflating because it was so cold outside. But the Patriots were used to having colder footballs, so they allowed them to grip them a little bit better because that's what they were saying. And that's a kind of funny real-life example to talk about with it. Okay? So Charles' Law. Charles' Law, the formula is V1 over T1 equals V2 over T2. So they're not being multiplied. We have to divide the volume and the temperature. So we look at what the situation is initially, and that's V1, T1. And then we say, what are we changing? That's either V2 or T2, and you solve for what's missing. Okay? So that's what we got there. There you go. Now, one of the things we do have to bring in now with Charles, okay, you got to make sure this adds one little step, is we have to be in Kelvin. So if you're given degrees Celsius, you need to convert it to Kelvin before you put it in the formula. If you use Celsius, it's wrong every single time. All right? Remember now standard temperature and pressure. Again, standard pressure, we're not going to have to worry about it, but if I say I do change something to standard temperature, that means I'm going to 0 degrees, which is 273 Kelvin. So that's where we might have to involve that. The graph, since they're directly related, if I increase the temperature, the volume goes up. So you see a nice straight line right here. Okay? They increase together. And now let's do a couple example problems, maybe 3 of them again. All right? I'll change colors, maybe white. I think white will look good. All right, a gas with a volume of 256 milliliters and a temperature of 25.1 degrees Celsius is heated to 35.8 degrees Celsius. What is the new volume? So you're being given volume and temperature. Again, you'll have all the formulas. You might just have to remember which one is like who's the who's. So V1, T1, V2, T2. So I have my initial situation where I have 256 milliliters and 25.1 degrees Celsius. All right. So I can put the 256 milliliters on top, but I need to change this temperature into Kelvin. My formula is Kelvin is 273 plus degrees Celsius. So I just plug that on in. 273 plus 25.1, that is 298.1 Kelvin. So that is my temperature that I'm going to put on the bottom of this. This equals, I'm solving for the final volume. All right, let's think about this real fast. The temperature's going up, which means the volume should go up. So I better have an answer bigger than 256. But let me get the new temperature. the new temperature, I'm using the same formula, 273, but this is now 35.8 degrees Celsius. So this would be 308.8 Kelvin. 308.8 Kelvin. All right. How do I solve? All right, you could either do, I mean, there's plenty of different ways. Some people do cross multiply. If you know how to cross multiply, you can just do that and set up the equation. So we do 256 times 308.8 equals 298.1 V2, and then I'd be able to divide out 298.1. All right, I'm going to just show it to you that way. If you want to choose a different way to do it, just get it right. I'm getting an answer of V2 equals 265 milliliters, which at least seems reasonable because I am increasing the temperature, so I should be increasing the volume. All right, let's try another one. A gas with a volume, basically the same thing. 2 liters, 32.5 degrees Celsius is cooled to 24.1, so my volume should go down. So V1 over T1 equals V2 over T2. My initial volume is 2.00 over 32.5 degrees. I need to change that to Kelvin. 32.5 plus 273. That is 305.5. And then I need to do V2 over T2. Kelvin equals 24.1 plus 273. That's 297.1. I can then cross multiply. 2 times 297.1 equals 305.5 V2 divided by 305.5. My new volume is 1.95 liters. It's liters because I'm starting with liters. Okay? You don't need to change the unit for that unless you're given the two volumes and they're different. All right? Let's try another one. What is the final volume of a gas that starts at 8 point... Oh, okay, I was like, that's weird. All right. What is the final volume of a gas that starts at 8.3 liters at 70 degrees and is heated to 96? So we know the volume is going to go up. We've now done this a couple times. So I'm going to just jump straight to the formula. 8.3 divided by temperature, 273 plus 17, that's 290, equals V2 over 273 plus 96. That's 260, what is that? Oh, 69. No, 369, sorry. 369. And cross multiply. 8.3 times 369 equals 290 V2. 8.3 times 369 divided by 290. V2 equals, I'm in 2 sig figs, 11 liters. And that's it. That's how we kind of handle that one. So we will continue moving on with our other gas laws in our next videos. Thank you.